All right, so in this next video, we're going to be talking a little bit more about pressure here with fluid mechanics. We're going to start off with a quick demo, and then we'll jump right into it. So let's go.
All right, so here we go. 3 holes, 1, 2, 3 at different heights on this can. We're going to fill this can up with water. I've put some blue food colorings in there just so that it's a little bit easier to see against the white background there. So hopefully you'll be able to get a good glance at what happens. First thing I want you to do is you make a guess. What do you think is going to happen to the water coming out of these 3 holes? And here we go.
So pressure. We've been using this word and talking about it a lot, but what we really want to do here is let's see if we can get some definitions down and get a formal way of describing pressure. Now, what exactly is pressure? Well, pressure is defined as force over area. So that's it. Pressure is the ratio of force per unit area. One thing to remember here is that the force is the force that is perpendicular to the area that we're referring to. All right, so that'll be important as we start to look at this a little bit more, is recognizing that we are talking about the component of the force which is perpendicular to the area. And we'll talk a little bit more about that later. So let me show you another demo to kind of demonstrate the big deal. Why do we even have another term here? Okay? So why do we even care? If pressure is just force over area, isn't it essentially the same thing as force? Right? Doesn't something that have greater force also have greater pressure? Well, think about it this way. It's similar to, remember back in AP Physics 1, we had F equals ma. Something that had a larger force would definitely have a larger acceleration, but only if the mass was the same, right? We have to pay attention to that other variable there. And so when we look at pressure equals force over area, just consider that idea. Think about the idea that force and pressure are proportional, but only if the area is the same. So here's a quick demo for that. Take your pen or your pencil, take the flat side here, and pound it against your hand. You can probably do that pretty hard. You feel pretty safe. You're not really worried about getting hurt. You can do it multiple times and pretty hard. Okay? Now don't do this, but imagine taking it and pointing it the other direction, exerting the same amount of force. Don't do it. Okay? But if you imagine doing that, you can think of, oh, well, there definitely would be a difference there. Right? Even though your force is the same, there would be a different result to the skin of your hand. Why is that? Well, because pressure equals force over area. And if the force is the same, and you decrease the area over which that force is being exerted, if I do it over this small area instead of this large area, if your area is small, that means the pressure is going to be much higher. So the pressure on that point of your skin is going to be higher and therefore could end up penetrating your skin. So that gives you at least one example of a situation in which we have to understand that if the area is changing, then force and pressure are no longer proportional in that way. And so that's why we care about pressure. Pressure can be different in many ways. Though we will make the connection a lot of times when the area is not changing, we will go straight from pressure to force and recognize that those things are proportional. All right? All right, so let's work through an example. Let's start to do a little bit more math here, all right? Consider a water bed laying flat on the floor. The empty bed has a mass of 10 kilograms, and the filled bed has dimensions of 2 meters by 2 meters by 30 centimeters, and they give us the density of water, which we're almost always going to assume is about 1,000 kilograms per meters cubed, and find the pressure of the bed on the floor. So first, let me start off by drawing a picture. Boop, there we go. So we've got our water bed. And essentially, in order to find pressure, remember pressure is force over area, which means that we need to find the force that the bed is exerting on the floor, and we need to find the area over which that force is being distributed. All right, we can do both of those. In fact, the area is pretty straightforward. It's just 2 times 2, right? So we get 4 meters squared. So that's the area of the mattress that is touching the ground. Okay, now we need to find the force that the bed is exerting on the ground. Now, if you think about it, if we draw a free body diagram, we have that gravity is pulling down on the mattress, and then the floor is pushing up on the mattress. Now, if we have those two forces, first we know that according to Newton's third law, if the floor is exerting a normal force on the mattress, then the mattress is exerting exactly the same normal force on the floor. Secondly, we know that because the bed is not moving, that the two forces must be balanced, which means that the normal force of the floor must be equal to the force of gravity. Therefore, if we find the force of gravity, we know the normal force of the floor on the mattress, therefore we know the force of the mattress on the floor. So, what do we need? We need the force of gravity. Now, to get the force of gravity, we know we have the formula Fg equals mg, and we have g. So what we need here is the mass. Well, I don't have the mass, but is mass connected to anything that we have here? Well, we have density. How is density connected to mass? Well, I know that density is mass over volume. So if I have the density, if I can find the volume, I can get the mass. All right, let's do it. Density equals mass over volume. So the density was 1,000. And the volume is 2 times 2 times 0.3. It's just a rectangular prism there. So what I get is that the mass is equal to 1,200 kilograms. Now that I have the mass, I can go ahead and put that into my force of gravity equation. I'm going to multiply that by 9.81. By 9.81, and I get about 11,800. It's slightly different, but at this point, I'm not going to worry about more than 3 sig figs. So 11,800 newtons. And now that I have that 11,800 newtons, that's the force, which I can now go, I can put that in for the force. I can put the area in here, and I should be able to solve by dividing by 4, and I get my final pressure now, and the pressure is 2,943. And then we got our answer, that the pressure is 2,900 newtons per meter squared. Now, you may ask, well, what are the units for pressure? Well, we already know that it's force over area, so you could do force, which is newtons, over area, which is meters squared. You can also use pascals, PA, and pascals is another appropriate unit. Now, one thing I would like to make mention of is this. I'm not sure if you noticed this, but let's go back to what we did. Let's work through this symbolically really quick. Remember, we got our force. The way that we got our force is that we multiplied the mass times gravity, and the mass was just the volume times the density. So mass was density times volume, and then we multiplied that by g for the height, and then we divided that by the area. Now, how did we get the volume? Remember, we got the volume by doing length times width times height. Now the length and the width are area. So essentially what we did is we multiplied the area times the height. So we can actually cancel those areas out. I don't know if you saw that here. Here is your 2 times 2. And then the volume there, remember the volume was 2 times, oh yeah, it's right there, 2 times 0.3. So we can actually cancel those out, and we end up with this, that pressure then is just density times G times the depth or the height. This is our first indication that pressure is going to depend on the height or the depth of which you are in that fluid. We're going to talk about this a little bit more later, but this is an important concept, and we're going to see this in a few of our examples here in a minute. All right? Now, before we go on, I do want to talk just a little bit more about the units of pressure, right? So we talked about the fact that pressure can be written as newtons per meter squared, and that newtons per meter squared, or force per area, can also be written as pascals. So just as with joules and all the other types of units that we've seen before, 1 Newton per meter squared is 1 Pascal. Now recognize that Newton per meter squared is not fundamental units. So I'd like for us to take just a minute, see if you can do this on your own, see if you can figure out how to rewrite pascals in only fundamental units. All right? Go ahead and see if you can figure that out. Hopefully you ended up with something like this, and you ended up with kilograms per meter per second squared. And there you go. That's pressure in fundamental units. Now, another type of units that's seen very often is called atmospheres. Okay, now atmospheres are used commonly because sometimes we just want a general number that compares the pressure to what we feel under normal atmospheric conditions at sea level. This unit, which we call atmospheres, is equal to 100,000 pascals. So this is just something you should be aware of. Note that 1 atmosphere is about 100,000 or 10 to the 5th pascals. This is a common type of unit that you'll see on AP exams and such, and you just want to be aware of it. This is on the front page of your AP formula packet, down on the page that has your constants and things like that. One of the conversions there that it gives you is 1 atmosphere. Okay, so it is there. It's just nice to be aware that that's something that you'll commonly use. All right, let's go ahead and move on to the next piece. So there's a couple of really important details that you want to remember about pressure. This is the first one. Pressure at a point is in all directions and is always perpendicular to a surface. Now in the drawing here, it's showing up as a cube, but we're looking at a single point in the fluid. So the pressure is acting on that point from all directions. Sometimes people have this concept that the pressure is pushing down. Well, gravity is pulling the fluid down, but when it pulls the fluid down, it actually causes the fluid to push on you from all sides. If you think about diving down in a swimming pool, you dive down to the bottom. It doesn't matter which direction you're facing. You can roll on your side or look up or look down. You feel the same pressure on your eardrums no matter what. There's no position that takes that pressure off. The reason being is because at that specific depth, pressure is the same everywhere. Now, this idea of always being perpendicular to a surface is important as well. If you think about the surface of your container right there, at that specific point, there should be pressure coming in from all directions. Except there's no fluid over on the left-hand side. There's only fluid on the right-hand side. So if we look at this, if you look at the components, the horizontal components are still going to be there, but the vertical components, at the bottom you've got a vertical component up, at the top you've got a vertical component down. Each one of these vectors has a vertical component that is going to cancel out. So the vertical pieces are going to cancel out, but they all have components going over to the left. And so the total pressure then should be perpendicular to the left. And that will be the direction of the force and therefore the direction of the pressure. All right. Now, the second point that I want you to consider and think about is this. At a given depth, pressure is always the same. Now that depends on the depth. That's what we found at the end of our mattress problem in the previous example, is that idea that the pressure depends on the depth. It doesn't depend on anything else. So those are big ideas when we're thinking about pressure. Now, the other thing that I'd like to mention before we go on is that, as per usual, we are going to be living in our perfect physics land. Right? In AP Physics 1, we did that a lot when we would do things like, let's ignore air resistance. We know there's air resistance, but we're going to go ahead and ignore it anyway. Or we assumed perfectly spherical objects so that there was less air resistance, the thing that we're ignoring. All those things we just kind of say, let's just pretend in this perfect world that these things are not here. So one of those assumptions that we make here is that we're dealing with an incompressible fluid. Now, this is important, that no matter whether we're using a gas or a liquid, most of the time the questions will specifically say, assume that the fluid is incompressible. Now, what that means is that no matter how much force or pressure there is, the fluid is not going to get more dense. It can't be compressed. That's what incompressible means. Now, of course, if you could change the density of the fluid, that's going to mess with our pressure, because the more dense it is, the more weight that it has, and so therefore you're going to end up with more pressure. And hopefully you've been able to see that as we've started to look at some of our equations and things like that, is that density is a big deal here. So we are going to assume constant density for most of these fluid questions. All right. So what I'd like to do now is introduce you to a couple of concept tests. Go ahead, flip on to the next page. Please try to answer them before you listen to the answer. All right? So in this first question, look at the image below. You've got some different colored fluids. You got points A, B, C, and D. Each one is under a different volume of fluid there. So you've got a bulb, a swirly thing, one that's just kind of straight at an angle there. So the question is, can you rank each of those points in order from lowest to highest pressure? All right, go ahead and give it a try. Now, hopefully you said this. Ta-da! Yes, all of the pressures are the same. Remember, we've been talking about this idea that at a given depth, pressure is always the same. If you look at each of these pictures, the depth of A is the same as the depth of B, which is the same as the depth of C, which is the same as the depth of D. It doesn't matter how wide that depth is. It doesn't matter how much distance it travels through to get there. None of that matters. All that matters is the depth. And all those points, A, B, C, and D, are at the same depth. Therefore, they must have the same pressure. Let's try another. So one more in this concept test. Each of the containers below has the same fluid under the same conditions. Again, incompressible, so constant density. Considering the pressure at the bottom of the container, rank them from highest to lowest pressure. Give it a shot. So hopefully you're recognizing that at the bottom of the container, regardless of the shape of the container, the depth is the same. And what does pressure depend on? Pressure depends on depth. The area doesn't matter. Remember, the area is going to end up canceling out. The area does not matter. So therefore, all four pressures are equal. Now, I know it's really tempting, for example, to say, yeah, but doesn't 3 have more water on top of it? Well, that would be like saying that going swimming in the ocean means that there's going to be more pressure than swimming in a swimming pool because the ocean's wider. Yeah, that doesn't make any sense, does it? You still have to dive down a certain distance in order for you to start feeling the pressure of being underwater. So it really doesn't matter what the shape is. All that matters is your depth. All right, so that's given you a pretty good introduction to pressure. We're going to go ahead and in the next video, we'll talk specifically more about Pascal's principle. All right, so see you there.